Hey everybody, this is the first of the three videos I'll be making for some extra exam prep for this final exam in Calculus 1, Fall 2025. So for this first set, I'll be going through Learning Target 8, which is all about related rates. So the way I've set this up is we'll have three problems we're going to look at least for this topic. The first one, this is the problem that we saw in checkpoint 3. So you're a bit familiar with it, but I thought I'd just go through it and show you how I did it, maybe some tips and tricks along the way. If you haven't already, I would take a look at the document for this, try to solve these problems yourself, and then use this video sort of as a reference and like a little bit of a key. It's posted to the class Canvas, I think in an announcement, or maybe it's somewhere in the files, depending on when you're seeing this. And I'll also try to link this document to the description down below. So let's just jump into it, I guess. We have a rectangle where the length is increasing at a rate of 8 centimeters a second, and its width is increasing at a rate of 3 centimeters a second. And we need to find how fast the area of the rectangle is increasing when the length is 20 and the width is 10 centimeters. And we're given that the area of a rectangle is L times W, its length times its width. So the first thing we want to do is put down our givens. And in this case, you're given the rate of change of the length and the width. So we have that dl, change in length, dt, with respect to time, is 8 centimeters a second. I think it's always good to keep track of your units as you go along. It'll help you at the very end confirm that your units add up and match what you're expecting for your answer. So we also have that dw dt is 3 centimeters a second per the problem statement. For our unknown, we are looking for how fast the area of the rectangle is increasing. So that makes me think dA dt. I'll also note this is when the length is 20 centimeters and the width is 10 centimeters. So for the equation, this is pretty easy. It's given up here. We have that A equals L times W. Okay, now we need to differentiate both sides with respect to t. So we have d dt of A is going to be equal to d dt of L times W. So left side of this equation, that's pretty easy. d dt of A is just dA dt. But with the right side, since we have two variables that we're differentiating, we need to remember to use the product rule. These related rate problems, it's been a while since we've done product rule, quotient rule, chain rule, but we still have to remember to think about them since they're all variables. We got to remember those rules and also remember how we do implicit differentiation because that'll come up not as much in this problem, but problems to come. So anyways, the product rule, we will have L times dw dt plus W times dl dt. Okay. This one's pretty easy with the arithmetic. We'll just be plugging in. So for our length, in terms of the unknown, the length will be 20 centimeters. So 20 centimeters times dw dt, which we have as 3 centimeters a second. And we're keeping those units in there. Plus W is 10 centimeters. Multiplied by dl dt is 8 centimeters a second. So dA dt is equal to 60 centimeters squared per second. That's because we're multiplying centimeters by centimeters per second. And then 80 centimeters per second squared. So this just comes out to be 140 centimeters squared per second. And a little bit of a unit check, sanity check. We get centimeters squared per second is the units. And we're looking at how fast area is increasing. That's a rate, so this makes sense. Area, I think, centimeters squared and per second. So that makes a lot of sense to me, at least. Um, Answer, the number seems reasonable. We defined all of our givens, our unknowns, our equation. We differentiated in terms of t and came to the final answer. So I'm pretty happy with this. Okay, let's move on to number 2 now. Uh, it says the title, Virginia 46, Florida State 38. So we have that on September 26, 2025, Virginia beat the number 8 Florida State Seminoles in an all-time classic at Scott Stadium when Castellanos threw a interception in the end zone in double overtime. Students poured onto the gridiron and was probably the best field rush of all time. So a little bit of intro there, but now we have that in the moments immediately after this upset, a student crossed the goal line onto the field at a constant speed of 10 yards per second. At the exact same instant, a blue firework was set off at the goal line, vertically into the air. So considering its initial velocity and the force of gravity, which you will look at in Physics 1, probably this spring, the firework can be modeled as having a vertical velocity of 40 minus 10t yards per second. And because of that, its vertical position would be 40t minus 5t squared, which that's just the antiderivative of the velocity function, but I gave it to you just to be sure, clear up any confusion. And it's asking us what the rate of change of the angle between the student and the firework will be when the student crosses midfield 50 yards from the end zone. Little note there with the trigger identity, we'll get to that in a little bit. But now I would say we just want to take a look at what we're given. So this one's not as clear exactly the equation we need to use. It's not given to us directly. So I'm going to set up a drawing. So I have a student. We'll say they're running this way. They're running from the hill or something at Scott Stadium. And we'll call this X. This is the X direction. And the firework that's shot up in the air, we'll call that the Y direction. And eventually we'll be solving for the rate of change of the angle between the student and the firework. So completing this triangle, we'd have this angle here, we'll call that theta. That's the angle. And what are we given? We're given the speed of the student. He's running at constant speed of 10 yards a second in the x direction. So we will call that dx dt. The change in the x direction with respect to time is 10 yards per second. And the firework going vertically in the air, that has a velocity or speed of dy dt being equal to 40 minus 10t. And that's also yards per second. With it being an equation, I don't really care as much about including the units, but it doesn't hurt. And we also have its position. That would just be y is equal to 40t minus 5t squared yards. And our unknown is that change in the angle, d theta dt. And that will be when the student is at midfield, which is 50 yards from the end zone. Okay. Now for this one, we have to think a little bit more about getting our equation, but we have theta. So that makes me think trig. We're given a y value and an x value, where the y value is opposite and that x value is adjacent. So I'm going to go with tangent. We have tangent of theta is equal to y, which is opposite, over x, which is adjacent. So now we need to differentiate both sides with respect to t. So we have ddt of tangent of theta, and that is equal to ddt of y over x. All right, the derivative of tangent is secant squared theta. And since tangent is a function of theta, but we're deriving in terms of t. We need to use our implicit differentiation and include a d theta dt term. And for the right side of the equation, I have y over x, which makes me think of using the quotient rule. So I have low is x times dy dt, it's derivative of high, minus high, derivative of low, over low squared. Apologies for writing a little bit small here. This question is a little bit of work in terms of the algebra and arithmetic, so I just want to make sure I have enough space at the end to solve it. Anyways, let's see, what do we have? We have x, we know x is 50 yards, that's given in the unknown. Y, up here, y is just a function, so we need to actually evaluate that. Same with dy dt, that's also a function, but dx dt, that's just a constant. But y is a function of t, and I don't really know a t value. I know that we're examining this problem when x is 50. We don't have the associated t. So let's think through that. Let's see. We know that students traveling at 10 yards a second, so that's velocity, and velocity is equal to distance over time. So I solve this algebraically. I have that time is equal to distance over velocity. I know that students traveled 50 yards, and he's traveling 10 yards a second. So this gives us t equals 5 seconds. That means 5 seconds have occurred since the student left the goal line. So what I'm going to do now is I'm going to plug that in to find y, the vertical position, and because it's y of t. Actually, we'll say y of 5 is equal to 40 times 5 minus 5 t squared, so that's 5 squared. And this is just equal to 200 minus 125. So y is equal to 75 yards. And just to be clear, I'm getting that from right here. That was in the problem statement. Okay. We also have dy dt. We haven't actually solved for that yet, or evaluated that yet, but that's also pretty easy. Dy dt, I guess it's a little bit confusing writing it like that. So I'll just say dy dt is equal to 40 minus 10 times t. T is 5. So we have dy dt is equal to negative 10. That's in yards per second. It's interesting. So this is telling us that the firework is going to have a negative velocity at the point that we're looking at, which I suppose makes sense depending on its propellant or anything like that. It could start falling down once it runs out of fuel and the force of gravity overtakes its initial velocity. But anyways, we now have x, we have dy dt, we have y, and we have dx dt. And we're going to be searching for d theta dt, but the secant squared theta term is still bugging us a little bit. But before going into too much, I'm just going to knock this out a little bit more algebraically and divide that over x dy dt minus y dx dt all over x squared. And that would be times 1 over secant squared theta. So at the beginning of the problem, I noted that secant squared theta equals 1 plus tangent squared theta. You don't technically need this for the problem. I think you could end up using the Pythagorean theorem to evaluate like this third side here, the hypotenuse side, but we're already doing a lot of grunt work in the process, so I thought I'd make it a little bit easier and save you that trouble. So instead of having secant squared theta, I'm going to replace that with 1 plus tangent squared theta. And the reason I'm doing that is because here we have tangent theta. We now know this, with it being y over x, this will be equal to 75 over 50, which is just 3/2. So now I think we can plug some numbers in. So we have x, which is 50 yards. And I'm going to try to keep the units, keep everything consistent. It is a bit of a pain, but I do think it's beneficial. It's a good check. If you get to the end and your units don't make any sense, then it means you probably made a mistake along the way. Go back and check it out. Okay, so dy dt, negative 10 yards a second. Minus y is 75 yards. Times the x dt, that's 10 yards a second. All of this is over x squared, which is 50 yards squared. Okay. This will be multiplied by that 1 over tangent squared theta, which is 1 over 1 plus 3/2 squared. That's the same as 9/4. All right, a little bit more to deal with. Oops, sorry, this is wrong here. 50 yards, quantity squared. I promise this isn't so bad though. We have d theta dt. We're nearly there, I promise. D theta dt. 50 yards times negative 10 yards a second. That's negative 500 yards squared per second. Minus 75 yards times 10 yards per second, 750. Oops, that's squared. Yards squared per second. All over 2,500 yards squared. And then times 1 over 1 plus 9/4, that's 13/4. All right, negative 1,250 yards squared per second over 2,500 yards squared. 1 over 13/4 is the same as 4/13. All right, so this ends up actually just coming out to negative 1/2 yards squared per second over yards squared. That's just 1 over second. That's s, 1 over second, times 4/13. And we're dealing with an angle here, and we always deal with radians when we're doing these type of problems. So you may be wondering, well, where is radians? But technically, radians are, I guess, dimensionless or unitless. So it wouldn't actually come up. Since it's a ratio of lengths, the units will cancel out compared to degrees, which are like defined. So we're not dealing with degrees. We don't have anything in degrees here. We're dealing in radians, so it's fine that it doesn't say radians anywhere yet. We know that we're dealing in radians, so we can effectively say that it's radians per second. But we'll have negative 1/2 times 4/13. That's the same as negative 4 over 26, or negative 2/13. And that's in radians per second. So, all right, I guess sanity check, radians per second, that makes sense. I explained why we get the radians sort of out of nowhere, but it's a negative number. It's a negative rate of change for the angle. Let's see, does this make sense? Looking at this problem, we know from earlier when you solve the velocity of the firework that the velocity is negative. It's negative 10 yards a second at the instant we're looking at, which means the firework is traveling downwards, which I suppose this makes sense that the angle between the student and the firework is decreasing. So negative 2/13 makes sense in the fact that it's negative. This problem is definitely a bit of a doozy in terms of what you're solving for. The way I organized it, you sort of had to solve for t first. You had to go and solve for y and dy dt. So it probably wouldn't be this complicated on the final exam, that's for sure, but I wanted to make sure that it made you think a little bit. We used the quotient rule, we used implicit differentiation, we had to consider units. So I think that was a helpful problem, or at least I hope it was. Yeah, that's the second one. Okay, done with number two, so let's give the third and final one a shot. Celebratory soft serve. So we have that after the big win over Florida State, the same student decides he wants to enjoy a huge soft serve ice cream at O-Hill in a waffle cone. This cone is 18 inches tall and has a top radius of 6 inches, and its soft serve is pumped into the cone at a constant rate of 10 inches cubed per second. And what will be the rate of change of the height of the ice cream when the height is 9 inches? So we're told to think about the relationship between the radius and the height, whether it's constant or changing, and also noted that the volume of a cone is given by v equals 1/3 pi r squared times h. Okay, so once again for the given, I'm going to draw a little picture of our waffle cone of sorts. It's a triangle, and we know that the height of the cone is 18 and the radius is 6. Both of these are in inches. Sorry, but yeah, inches, yes. It's a big waffle cone. And dv dt is equal to 10 inches cubed per second. And we want to find dh dt when the height is 9 inches. Okay, so we also need to think about the relationship between the radius and the height. So if it's going to be a constant ratio or changing. So let's say I have some sort of triangle like this. And what if I shrunk down? So similar triangle. So what I notice is that the height and the radius, let's say we shrunk it in half, that ratio is going to be constant. What that means is h over r is a constant value. So in the case of our waffle cone, we have 18 over 6, which is equal to 3. So what this means is that we could write r as 1/3 h, or h is 3 times r. Okay, so with our equation, we have that v equals 1/3 pi r squared h. And that means v is in terms of r and h. And thinking ahead a little bit here, we're going to be searching for dh dt. But I'm not given anything in the given or anything in the problem statement about dr dt. So thinking ahead, if it were to differentiate both sides with respect to t, I'd have a dr dt value as it stands. But I'm not given anything about dr dt. So that's where these relationships come in. So I have two relationships, one h in terms of r and one r in terms of h. And I know that I'm going to be searching for dh dt, which probably means I want this volume function in terms of h. So I'm going to be using this expression right there, that equation right there. So that means v is equal to 1/3 pi. R is 1/3 h. That quantity squared times h. So v is equal to 1/3 times pi. And then 1/3 squared is 1/9. H squared times h. So v is equal to 1/27 pi h cubed. All right, now v is in terms of just one variable h. So let's differentiate both sides now. We have d dt of v is equal to d dt of 1/27 pi h cubed. Okay, implicit differentiation, we just have dv dt, easy enough. Pretty easy on the right side as well. Pi over 27 That's a constant, so we just keep that out front, or constant coefficient. And then derivative of h cubed is 3h squared, but implicit differentiation rules times dh dt. And that dh dt is what we're solving for, so we need to do a little bit of algebra here. I'm gonna basically just get dh dt on its own, which means we still have the dv dt, multiply over that 27 and divide by the pi, and also divide by 3h squared. And we know dv dt, that is 10 cubic inches per second. 27 over pi, that's all unitless. And then 1 over 3h squared, where h is 9, right? Did I say 9? I did. 9 inches squared. All right, so 10 inches cubed per second times 27 over pi times 1 over 27. Whoa, nope, sorry. 3 times 81 inches squared. Okay, instead of just multiplying out all these big numbers, I have 27 divided by 3. That's 9, so I would have 9 over 81, which is just equal to 1 over 9. So that tells me dh dt is equal to 10 over 9 pi, and inches cubed divided by inches squared leaves me with inches per second. And then sanity check, inches squared, I'm looking at the rate of change of the height, so that makes sense, inches per second. I might have just said inches squared, I'm sorry if I did. I meant inches per second is what we're looking at, inches per second. Yep. So positive value for dh dt, that makes sense. The height, the rate of change of the height is increasing when height is 9 inches. And yeah, I think this problem isn't too bad. It's making us think about the relationship between the radius and the height. You know, we might have seen this equation here and just differentiated that, and we would have dr dt, and that'd be a little bit trickier to deal with since we didn't actually have an explicit value for that. So in that case, just setting up this relationship first and subbing in gives us an equation that's easier to deal with when we differentiate. But that is the end of this video for related rates. First one, checkpoint 3 problem, pretty simple. We've seen this one before. Second one about the student and the firework, definitely a little bit more work to it, but I think it was pretty valuable just for recognizing what's given, recognizing what we need to solve for, and just sort of thinking outside of the box. And then third one, also pretty standard, just geometric relationships, but still a worthwhile question. But overall, not too bad. If you have any questions, I think my email is somewhere on the Canvas page, so shoot me an email if you need it. But other than that, yeah, thanks for watching.